Hello everyone. Today we are going to discover how to find the electrical field due to a system of discrete charges. Suppose that we have a system of discrete separate charges Q1, Q2, Q3 and Q7. Each one of them is intuitively going to create an electrical field around it, and we wish to find the net electrical field at some point P, which is an arbitrary point which is located in the free space. In order to find the net electrical field at this point, we can use this formula. We can find the electrical field generated by each charge, then take the vector summation and sum all of these contributions of electrical fields. Then at the end we will reach to this formula where r minus r sub k prime is the vector which starts at the charge point and at the charge and points toward the point, and this modulus of this vector is the distance between the charge and the point P. Anyways, although this formula looks concise and simple, it's inconvenient to be used because of the need to add vectors of different magnitudes and directions. Therefore, this trouble prompts us to formulate a better approach to find the electrical field due to a system of discrete charges. Now, let's consider a simple case of system of discrete charges. We will consider an example of electrical dipole, as electrical dipole consists of a pair of two opposite charges, two equal and opposite charges, plus q and minus q. These charges are separated by some distance. We will represent this distance by d. Okay. Also, d is a vector which starts from minus q and ends at plus q. Okay, and we want to calculate the electrical field at P due to plus q and minus q. Firstly, let's determine the location of the origin. We will make the location of the origin at the center of the distance between plus q and minus q. Let's make the origin at this point. This is the origin, and according to the origin, we will separate this vector into two vectors. The first vector, which starts from the origin and ends at minus q, and as this vector has an opposite direction to d, this vector has magnitude of minus d over 2, as minus d over 2 means that this vector has magnitude or length equals to the half of this vector d. And the other vector, which starts at the origin and ends and plus q, it has the same direction of d, so it's positive like d vector, and it has the half of length of it, so it has the magnitude of d over 2. It's positive as we aforementioned. Now we will determine the location of the vector P with a vector. The vector position of P is usually represented by r vector. This is r vector, which starts at the origin and ends at point P. And in order to find the electrical field at P due to plus q and minus q, we will use this equation. And as we see in this equation, we need the vector which starts at the charge and ends at the point. So we need to determine determine these two vectors. And as we see, according to tip to tail, this r vector you see this R vector, which is the vector at the half, equals to the summation between this vector and this vector. So this vector, this new vector, this new lower vector is equal to the magnitude of R plus d over 2. To check this out, try to add this, and the answer of the summation, the answer of the addition must be equal to R. And also this, the summation between d over 2 and this vector equals to R. So this vector is equal to R minus d over 2. So now we are ready to apply this equation. And as we said, the electrical field at P is equal to the contributions due to these two vectors is outward. We have the first electrical field is outward due to this, and it's along this vector, okay, and it's inward due to this because it's negative. It's also along this new vectors. So the electrical field is equal to the summation of these two electrical fields. As we see, Q and 4 pi epsilon are constant, so we can take these four of them as a common factor. Q over 4 pi epsilon 0 equals to, so the is equal to the electrical field due to plus Q is equal to R minus D over 2 divided by R minus D over 2, and as this is cubed, this denominator is cubed, minus the electrical field due to minus Q D over 2. Okay, that's good. This is the electrical field at P due to these two charges. We can make a few simplifications on the denominators right there, and we can take the advantage of something. The distance between these two charges, which is d, is significantly less than the distance between the point and the center of the dipole, which is r. Okay, so according to this, we can simplify these two denominators. I will start with this one. And I prefer to transfer this to the numerator and make the exponent negative minus 3 equals to, I will take the square of this, and then I will take the square root of the whole of this whole term, and I will have, let's not forget the vectors. And as I take the square, I will put the square root out minus 3 over 2. Now make the multiplication, and as R and R, these both of them consist of a product of some scalar value and unit vector. Okay, and this has is the same thing, scalar value and unit vector. When we make a multiplication between both of them, this unit vectors is going to vanish. Okay, and this still, so when I multiply the vector of R times vector of R, I will end up with only R squared without bar, without the unit vectors, and minus R dot D plus D squared over 4. And as we said, R is significantly greater than D, so this term is infinitesimal when we compare it to R squared and R dot D. So this is going to vanish. It has no significant effect on this, in the whole on this formula, so we can write this formula without this. We can drop this. So this is approximately equal to r squared minus now I will take r squared out of as a common factor. Okay, that's cool. Now I am going to simplify this. Sorry, just let me take another paper. Yeah. Now I can simplify this using the binomial expansion, and I will write there in this paper, I will write the formula of the binomial expansion. As we see, 1 plus x to the power of n is equal to this series, which continues until infinity. So we are going to apply this this expansion upon this this equation. In this case, n is equal to minus 3 over 2, and the x is equal to r dot d divided by r squared. Let's apply this, and we will reach to this r minus d over 2 or minus 3 is approximately equals to. Let's apply the binomial expansion, and we will have as we see, I applied this binomial expansion upon this, and I only took 3 parameters. Okay, and as we see in this series, the higher orders is negligible, has a negligible value. These values are significantly small when we compare it with these two terms, so we can drop this term and the incoming terms, and this is approximately equals to r to the power of minus 3 times only these two parameters, 1 plus 3 over 2 r. And as we see, we reach to a better approximation for this formula, and we are going to apply the same operations we did for this. We will apply these same operations for this. We will apply the same operations we did for this denominator to the other denominators, and as we see in this paper, there's no need to repeat them. Just we did the same things. We take the square of this, and then we take this and we put a square root out of this brackets. Then we apply the Taylor series or the binomial expansions, and we eliminated the higher order terms, and we will end up with this. Okay, and as we see, we have these two terms. I will write both of them beside each other, and as we see, these two we are going to substitute these new two parameters. We will substitute these two parameters for these two parameters inside this equation, and at the end we will end up with this nice approximation. E is equal to is approximately equals to q over 4 pi epsilon times r cubed times. And as we see, this is the electrical field due to these two dipoles. This form of equation is simpler than this one, and it's easily to be, and it's more applicable than this. Now, although this equation is good and simple, but it consists a vector manipulation, which is something kind of hard. So we want to use to make another simplification. We can use the concept of electrical dipole moment. The electrical dipole moment is a vector which is represented by P. It equals to Q, which is the charge, times the displacement between the negative charge and the positive charge. So we will use this, and in order to write this equation with in terms of P, we are going to multiply this Q with D in this brackets. So we will have now, as we said that the displacement D starts at minus Q and it's at plus Q. Let's assume that this axis is the z-axis, and this angle is the polar angle theta. So it's clear that we are considering our problem with the spherical coordinate system. So D is towards z direction, so P is towards z direction. So this P vector is equal to A sub z, as it's directing along this positive z direction, times P, which is the magnitude of this vector. Okay, and R vector, and this R vector is directing along the radial vector, which is this vector AR, A sub R times R. Okay, now I want to represent this A sub Z using R and theta vectors. Okay, I will represent the unit vectors on this point P, but I'm not going to write this point P right there. I'm going to write this there to make my explanation more clear. We said that R vector is radial. Its unit vector AR is like this, A sub R. Okay, and theta vector is moving like this. Okay, it's moving toward this direction, and it's orthogonal or perpendicular on A sub R, so it's something like this. Okay, this is A sub theta cap. This is the vector of the polar angle, and Z is upward, is like this, is along this. Okay, so A sub Z, the angle between A sub R and A sub Z, is equal to this angle. As we see, this is so clear because AZ is upward, it's like this, yeah, and the angle between this and this, between AZ and AR, are theta, so this angle is theta 2. Okay, so according to this, we can represent the electrical dipole moment P, which is along this direction, by, well, let's take P as a common factor. A sub Z is equal to a sub r times cosine theta. A sub z is equal to a sub r times cosine theta plus a sub theta times the angle between a sub z and a sub theta. The angle between a sub z and a sub theta is theta plus pi over 2. As we said, these are perpendicular, so this angle is pi over 2 or 90 degrees. So this angle, the other term of a sub z is equal to a sub theta plus times cosine theta plus pi over 2, which is minus sine theta. Okay, minus a sub theta times sine theta. Now we are going to plug these parameters inside this equation, and let's firstly make a dot product between r and p, r dotted with p. When we make the dot product, this term will vanish because we don't have a theta component inside this equation, but we have r component only. So and also unit vectors are going to vanish also. So we'll end up with r times p times cosine theta. Okay, now we are ready to plug all of these inside this equation, and we will have at the end E is equal to P over 4 pi epsilon sub 0 times r cubed times a sub r times 2 cosine theta plus a theta and of course, as it's electrical field, it's measured by volt per meter. For simplicity, I dropped this approximate sign, which is like this. I dropped it for simplicity, and that's the end. Thanks for watching. See you later in another video.